Hey there, I know what you're thinking. No, this isn't some weird alternate reality where everything is jiggly wiggly. What you were seeing were gravitational waves. Let's take a look at what they are. We seem to know how gravity works. Stuff falls down, right? Like this apple. Well, this is what Sir Isaac Newton said, and his law of gravity worked pretty well at usual daily life scales. But Einstein showed that gravity was actually a curvature in space-time. Sounds like jargon?
Space-time is the fabric of the universe. It is where everything happens. A heavy mass can curve space-time much like a heavy mass placed on a stretched cloth. Other masses tend to fall in towards it as if pulled by some force. This was the force of gravity as explained by Einstein in his general theory of relativity.
But what does this have to do with gravitational waves? Gravitational waves are ripples in space-time. Traveling at the speed of light, they pass through nearly everything. They tend to squeeze objects one way and stretch the other. We know water waves exist because we can see them. But what about gravitational waves? Say I have a couple of balls which I throw at right angles to two of my friends who are at equal distances from me. If I throw them at the same speed, they receive the ball simultaneously. If they also throw the ball simultaneously at the same speed, I receive the balls at the same time too. Say one of them moves away and the other one moves closer. Now if I throw the balls and they throw it back as soon as they receive it, there will be a time difference between the times that I receive the balls. This is the concept on which LIGO works. LIGO stands for Laser Interferometer Gravitational Wave Observatory. This is a representative diagram of the LIGO detector. A beam of light is split into perpendicular directions by a beam splitter, and after reflection from mirrors at the end of each of the two arms, they converge to a photodetector which receives the signal simultaneously. On the other hand, if a gravitational wave passes through the instruments, the distances will change. And since the speed of light is constant, the beams will not reach the photodetector simultaneously. And thus, we can know that a gravitational wave has passed. All good, but how are they produced? The simplest system that can produce gravitational waves is a system of two bodies orbiting each other around their common center of mass. A fairly common example is binary stars. If the two objects are black holes, then there is intense energy emitted in the form of gravitational waves, something like this. A black hole merger was the first event that helped LIGO detect the evidence for the existence of gravitational waves. When Newton gave his law of gravity, he revolutionized the scientific world. When Einstein gave his general theory of relativity, he brought about yet another revolution. And today, with instruments such as the LIGO detector, the doorways to understanding the cosmos lay open before us.